We have a lot of good topics lined up, a lot of good speakers. You're going to hear about network security and what the trends are for that and what the future holds for it. We've got a tech trends panel, which we have some good panel members on that, so you'll hear about some of the tech trends, some of the challenges of implementing the new cybersecurity products that are out in the market today. We also have a remote robotic process automation track. So this is an up-and-coming technology. I think it should be very interesting to everyone to see what that means and what it means from a security standpoint to your networks. We also have a future network security, cybersecurity as our last track. So we got a lot of good information, and we have a great keynote speaker today at noon, I think at lunchtime, Dick Schaefer, former IAD director of NSA. So he'll give you his insight, and I'm sure his uncandid insight on where he thinks cybersecurity is today in the federal government and what some of the challenges are. Let's see, I got a few notes here I have to do. Allison gave them to me. First, we'd like to thank our sponsors, Interseed, August Shell, and Norseman for sponsoring the event, helping us sponsor this, and our co-host, Carasoft, who you met most of the people outside when you registered. We also have a skills station introduction. Basically, there's stations set up outside. I think all of you got a card, maybe, to get stamped. So if you go watch the demos at each of the skill stations, get all 3 stamped. At the end of the day, we're going to have a raffle and give away some gifts and stuff for the raffle winners. So we're pretty excited. We'd like to make this a collaborative day for you guys. So in other words, ask a lot of questions, right? The speakers are up here to kind of give their point of view, but I think there's a wealth of knowledge, and we'd like to hear from everyone in the audience here on what their challenges are, where they see it going from a cybersecurity standpoint, and what some of the roadblocks are for implementing some of the technologies that you're going to hear about today. So let's make it kind of a collaborative effort today, and everyone have a good time. So with that said, I'd like to introduce our first speaker, Julian Frey. He's the CTO for Civitas. They're a very close partner of ours, and Julian's got, I think, well over 25 years of experience in network security, leading some high-level technology with Civitas and their products that's been deployed across the federal government, the DISA backbone, as well as a lot of other places, I guess, within the federal agencies, as well as commercially, a lot of banking and stuff. So help me in welcoming Julian, and we'll hear a lot about our network security.
Thank you, Kirk. Good morning, everybody. Good morning. How are you doing? Okay, right. Can we see the slides? It's coming. I'll just do a little song and dance. So a very quick introduction. It's a real pleasure for me to be here this morning at the SafeNet Cipher Summit for 2019. As Kirk said, my name's Julian Frey from Civitas. We're an Australian headquartered company, and we're very proud that we've been a partner of SafeNet's for more than 15 years. I've got a very strong technical relationship with these guys, so it's a real pleasure to be invited here. So, for those of you who may not know much about Civitas, we are a crypto company, which it turns out is actually pretty cool these days. Oh, goodness. All the cool kids apparently want to work in crypto. And I find that when I go to like a barbecue or a family event in Australia and people say, "What do you do?" I say, "I work in crypto." And you know, this strange thing happens. I've been doing this for 20 years, and suddenly I am no longer the biggest nerd in the room. People are actually interested in what I do. And they ask these questions like, "Oh, you work in crypto, so how early did you get in Bitcoin? And what do you think the price is going to be at the end of the year? And what the hell is a smart contract anyway?" And I don't have the heart to tell them, of course, that I'm actually in the wrong type of crypto. I'm in cryptography, the boring side of the business. But I never tell them that because that would make me no longer cool. So, but all jokes aside, you do have to actually be very careful about that terminology these days. I was struck by something that happened, I think it was in Washington just a few weeks ago. A lady called Ann Neuberger, who is the director of the National Security Agency's new Cybersecurity Directorate, was talking at an event, and she explained that the National Security Agency is working hard with NIST to develop new standards for quantum-safe cryptography, which is a great thing. You'd kind of hope and expect that the NSA is working on quantum-safe cryptography. So a journalist was at this event, and he tweeted, quite interesting, please note the agency is working to build quantum-resistant crypto. Nothing unusual about that. Except that's not what got reported. No less an organization than Forbes magazine reported this. NASA is developing a quantum-resistant cryptocurrency. Okay, so wrong agency, NASA, and wrong type of crypto. You might argue this is kind of the textbook definition of fake news. So you've got to be very careful. So the topic of this presentation this morning is the future of network security. And, excuse me, what I'd like to do is I'd like to talk about some of the trends that I see that are emerging now that are driving the way that we are using networks and the way that we will use them and continue to build them in the future. And then particularly what that means for our security of those networks. So, for example, an emerging trend is, or sort of emerging technology is the imminent arrival of 5G connectivity, which I believe is going to be a game changer. 5G is sometimes called wireless fiber, and it promises to give us a very high-speed mobile connection that will be somewhere between 10 and 100 times faster than our current mobile connectivity. And more than that, that network will be very reliable and it will have an extremely low latency. So that's likely to be an enabler for a whole range of new and emerging technologies, including autonomous vehicles, large sensors of IoT devices, and then whole new areas like remote telemedicine or remote surgery using micro robots. In fact, I saw an article recently about a Chinese surgeon who performed a very complex surgical procedure using robots over a 5G connection. And he was able to do that because the end-to-end latency across that network was about 2 milliseconds. That sounds pretty amazing, right? But the cybersecurity practitioner in me kind of stops there and pauses and thinks, okay, what does that mean for security? What would happen if someone were able to hack into that link whilst the surgery is being performed? What would it mean to even perform a simple denial of service attack on that 5G network? Obviously, the implications will be devastating for everybody involved. So there are a lot of emerging technologies that I think really do raise profound questions for all of us who work in the cybersecurity industry. So I want to talk a little bit about those. And then I want to spend a longer time talking about one emerging technology that is particularly interesting to me and to our business, which is the rise of quantum computing. But let's start by talking about the internet. In my opinion, the internet is probably the most successful and fantastic lab experiment in the whole of human history. Today, everybody in this room enjoys a myriad of amazing services that we take for granted every day. The ability to stream video on demand, anywhere, anytime, on a tiny handheld device. The ability to have free phone calls with anybody in the world. The ability to play rich, immersive online games with virtual realities, and the ability to have face-to-face video calls with friends and family wherever they are in the world. This rather grainy photo here, my apologies, was taken by me just a few days ago when I was unexpectedly invited to take part in a 6-way video call with some friends and family of mine. At the time, I was at a Marriott hotel in the middle of rural Illinois on a pretty dodgy Wi-Fi connection. Suddenly this call popped up, group chat, please join. I was in bed, as you can see. So I joined and I had a chat with 6 friends and family. There were people on that call from Hong Kong, there were people from the US, there were people from Australia, and we had a lovely chat and a great experience. Even a few years ago, this would have been science fiction, quite amazing. But those services are not what's really interesting. What's really interesting to me is that the internet was never built with those services in mind. The founding fathers of the internet probably couldn't envisage many of the services that we run on the internet today. And the lowest layer of protocols on the internet, the TCP/IP protocols, know nothing about video or voice. And that seems counterintuitive. You would assume you would have to build these capabilities into the fabric of the internet. In fact, the internet isn't even a single physical network, obviously. It's actually just a collection of disparate networks that makes one simple promise. And that promise is that it will make a best effort, an attempt, to deliver a packet from point A to point B. Now that doesn't sound like a pretty good foundation to build these kind of services upon. But actually I would suggest it is the foundation for the whole success of the internet. Because what we found out is that we can take that very simple capability, and as capacity grows, we can build extremely smart software, and if necessary, smart edge devices to allow us to build these very rich services. And that's an amazing thing. And it used to be the case that we would have a very clear separation between the internet and the enterprise wide area network. For more than 30 years, most enterprises were leasing MPLS services from carriers and using those for their enterprise traffic. One trend that I see these days is a real blurring of the line between the internet and the enterprise WAN. The internet is possibly the future of the WAN, although I don't think it will completely replace private services. I read a survey recently that said 80% of organizations are increasingly using the internet as their primary WAN connection. And the reasons for that are probably pretty obvious. If you're a digitally connected organization, which let's face it, we all are, it doesn't actually make sense to have a private network if you're trying to reach into cloud services or SaaS applications such as Office 365 or Salesforce. So we've seen the emergence of technologies such as SD-WAN, where we no longer have a single network transport. We can take advantage of a whole range of different network connections, including broadband internet, wireless, as well as our traditional MPLS networks. But again, as security practitioners, we have to ask, what's the security impact of this? Are we now worse off because we're going over a public network rather than a private network? Well, I would suggest in this case it doesn't actually make much difference. Private enterprise networks always held the promise of being more secure, but they were never provably more secure. Carriers, anyone with lawful access to the network, anyone with physical access to the plumbing of the private network could of course tap into or have access to even a private enterprise service. And almost no carriers around the world that I know of offer a by default encrypted service to their enterprise customers. So it was always the case that you had to encrypt your enterprise network, and we also, of course, have to do that when we send traffic across the public internet. It's just that the way that we do it is going to have to change, and I'm going to talk a little bit about that in a couple of slides. Another trend that I've noticed is essentially the rise of parallel internets. Does anybody have any idea what this event is? This is the League of Legends World Final. League of Legends is one of the most popular online games at the moment. This is the World Final. You cannot get tickets to this event for love or money. It sells out within minutes. More people watch this event online than watch the Super Bowl. These sports are fantastically popular and growing at an exponential rate. Esports players are now officially recognized by the US government as professional athletes and have the same visa rights. In short, this stuff is massive. Now, there are hundreds of millions of players who play this game around the world, including, as it happens, one teenager in Melbourne, Australia, who happens to be my son. And to be honest, he probably plays a little bit too much for my liking, but it's okay, it keeps him happy. But I have to admit, his playing this game does always cause some friction in our relationship. So I'll paint the scene for you. I'm working away hard in my study, working hard on crypto, and all of a sudden I'll hear this plaintive cry from his room. Dad, why is the beep beep internet so slow? Now, just a bit of cultural context for you. Beep beep is an Australian phrase that expresses the frustration of a teenager who's not getting what he wants. You can put in your local curse of choice. So it turns out, of course, that what he's experiencing is what is called lag in video game parlance. So those of you who are as old as I am, do you remember when the internet used to look like this? Do you remember when you used to click on a video and you would get this kind of spinning dial as the video would load. Except for him, he's a wizard in some fantastic world, and he's trying to cast a spell, and the spell won't cast, and he gets very frustrated. So lag is a bad thing, because lag leads to lag rage. And that's not healthy for the relationship between a father and his son, or for the bank balance of the father, if I'm honest. So the developers of these technologies obviously realized that this was a major problem. And although I said earlier that the internet has a very simple foundation and we've been able to build rich services on it using very smart software, it turns out that for applications that require very low latency, we are very challenged in using internet backbones to do that. We can put CDNs on edge devices to buffer video, but if you want a real-time rapid response, for example, for applications such as remote surgery or playing video games, that's a challenge. And you can see the problem here. You've got a video game player on the left. He connects to the network over some ISP network, and then the packet has to traverse the internet to get to the game servers, which in this case are in Chicago. And depending upon the vagaries of the internet on that day, the packet may take the path shown in green, or it may take the path shown in red. There might be a DDoS attack happening on some part of the internet, and you get basically a variable performance, and ultimately that leads to lag rage and makes these video games really challenging to build at scale. So Riot Games decided that they were going to do something about this. So they basically decided to build their own private internet. So what they did was they engaged in peering relationships with every service provider in every major city in the US. They leased space in data centers, and they put their own routers in those data centers. And then they bought or leased dark fiber from those data centers straight back into their servers in Chicago. And they transformed this into this. Very, very simple. And on the day that they turned this on, the average latency across their 100 million player database, at least in the US, dropped significantly, and the number of phone calls to technical support also dropped off significantly. Now, you wouldn't be surprised to hear that all of the large hyperscale players, Google, Microsoft, Amazon, have their own private internets. They're all built their own private internet backbones. Cloudflare, you've probably all heard of Cloudflare, has a global private backbone. Some of these organizations even run their own protocols across these backbones that may be more efficient than TCP/IP. There's a startup called Teridion that is basically building enterprise WAN across 25 private backbones from 25 different public cloud providers. This is very different from leasing an MPLS service from AT&T or from Verizon. In fact, Azure announced just a few weeks ago that they are now starting to offer a virtual WAN. This is a new WAN service from Microsoft. It basically provides branch connectivity across Azure's private backbone. And you can connect into this private backbone either over the public internet or via direct express route, in which case your data isn't even necessarily touching the public internet at all. So very, very different models. And I guess the question is, how does that impact security and the way that we encrypt and protect our data on these networks? Because you've got to ask the question, what's the point of these gaming companies and these hyperscale providers building very low latency, very efficient networks where we can take advantage of multiple transport types if we still keep encrypting the way we've been doing for 20 or 30 years, putting a 50-byte IPsec header on the front of every packet? We need solutions that have extremely low latency, that are optimized for these new network models, and that are very, very efficient in all use cases. So one trend that we're starting to see is the rise of what I call tunnel-free encryption. In a traditional SD-WAN or IPsec solution, we're always using some sort of tunnel or encapsulation overlay. In simple terms, we start with a simple IP header, a packet shown at the top here on the left, and as the network flows through the protocol stack, we start adding more and more data in front of that packet to get it across the network and to add security, until your 100-byte packet that you started up here ends up being 200 bytes or 300 bytes at the bottom, and you've doubled the effective throughput across that network for no real customer benefit. And of course, this leads to many ongoing knock-on effects, such as fragmentation issues, because large packets, if they exceed the MTU of the network, can't be carried across. You obscure the traffic flows of the data that's inside those, which might be important for some use cases. And basically, you've instantly clawed back all the benefits of these very low latency, very efficient networks. There are a lot lots of benefits to doing this in a tunnel-free way, which is a far more efficient way to encrypt data. If you can encrypt in a way that minimizes the overhead of your encrypted data, you can reap a lot of benefits. Obviously, you get far superior performance, especially over low bandwidth links, and you can avoid any fragmentation issues that might occur if you're doubling the size of the packet across the network, and therefore prevent replays and retries. It's estimated that tunnel-free encryption introduces a 40% performance overhead over tunneled schemes, which translates directly back to improved application performance and allows other benefits such as traffic flow optimization within the core network, because you can expose the protocols, if required, that traverse the network. Another security trend is that if we're going to have very large networks, imagine hundreds of thousands of IoT sensors, we need to completely rethink the way we do key management. In a traditional IPsec encrypted WAN, we would do key exchange on a peer-to-peer basis between every node in the device, in the network. So if you have n nodes in your network, you've got an n squared relationship between the number of key exchanges you need to perform. That very quickly gets out of hand on large-scale networks. So we're starting to see some trends to greatly simplify key management. One of the approaches is called derived keys. You start with a highly secure key from a NIST-approved deterministic random bit generator, and you load that into an appliance, and from that key, you can securely derive consecutive keys and minimize the amount of overhead that you have to introduce across the network and simplify the scalability problem. So we're starting to see a lot of trends happening in the key management space as well. We've thought about this long and hard. So we've taken into account those trends of tunnel-free encryption and new key management, and our solution is what's called tunnel-free transport-independent encryption. And we just have one very simple goal, which is to basically offer the most efficient encryption possible across the broadest range of possible network connections, whether that's at layer 2, layer 3, or layer 4. In other words, we want to remove any unnecessary overhead. When it comes to the drivers from a security perspective, I'll be honest, I think we've faced some pretty daunting challenges. Let's talk about some of the emerging technologies that are going to impact that. Would anybody like to hazard a guess what these two images have in common? Very many? They're images of people who don't exist. They were generated from a site called thispersondoesnotexist.com using a generative adversarial neural network. Pretty amazing, hey? I mean, I feel like I know that person. Yeah, right. Pretty amazing. Today, with artificial intelligence and machine learning, we're at a stage where we can train neural networks on millions of dollars of facial images. Not only can they actually pick out a dog from a cat or my wife from my friend and people we know, they can actually generate fake humans. I don't know about you, to me that looks very, very convincing. Even better, you can apply these same types of technologies on a single image to animate them. Here's an example of an adversarial neural network being trained on the Mona Lisa and generating an animated face from that single image. I don't know, again, I completely believe that that could be the person that's painted in Leonardo da Vinci's masterpiece. Pretty amazing. So, okay, these generative neural networks are kind of interesting, but they also pose us some challenges from a cybersecurity perspective. There was a story recently of a managing director of a company based in UK who got a phone call from his boss. And his boss had a strong German accent. And his boss rang him up and said, I want you to move some money. I want you to move several $100,000 from this account into this other account. And the manager went ahead and did it. Didn't think twice about it. He knew his boss had been working with him for years. And then a couple of days later, his boss rang again and said, I want you to move some more money from this account into this account. And he got kind of suspicious because the phone call he had an intuition the phone call wasn't quite as he expected. So he looked into it, and it turned out that an attacker had been able to record his boss's voice, maybe at a presentation such as this or on a YouTube video, and using an adversarial neural network had been able to create a deep fake audio that represented this boss's voice. And it was so authentic that it convinced the manager into actually transferring money. So ask yourself this question: if your